we are going to look at a proof using this triangle diagram. We are proving that segment RH is congruent to QM, and we have the givens that RD, which is this length of this triangle, and QD are congruent. M is going to be the midpoint of this side, H is going to be the midpoint of this side, and as always we want to assume that the diagram is not drawn to scale, so we're not going to believe it, but we can make little marks in here for ourselves that this and this should be the same length, strictly from the definition of midpoint, and that this and this are the same length, again from the definition of midpoint. And we can really start the proof beyond our givens at stating this fact that QH and HD are congruent and RM and MD are going to be congruent, and that is from the definition of midpoint. We can also follow up with a statement that QH and HD added together gives us the entire length QD, and RM plus MD gives us the entire length RD. So we're going to start there, and then we are going to do a little bit of algebra with those statements. All right, so now we have QH plus HD equals this, RM plus MD equals this and this are congruent according to one of our givens. So this total plus this total are equivalent to each other. Since this equals this and this equals this, then this equals this. And that's the next piece to this proof, is that we're going to set this equal to this by substitution. If these two segments added together equal these two segments, and we're going to do another substitution, and we're going to do it selectively using these ideas that we've already established through the definition of the midpoint to do a new substitution in here. And we're doing this selectively to get information about our diagram up here. We're going to make use of the fact that this is a little triangle down here, and also this is a little triangle down here. They share a common side, and so that's easy to argue that that side is the same length for both triangles. We can do that easily through the reflexive property. It would be good to also argue that this side is equal to this side, and possibly even this side equal to this side, or that some angle that we know in here is the same, so we can make use of triangle congruence arguments. Any of these things that establish that this triangle here is congruent to this triangle here, so triangle RQH being congruent to QRM, will give us this idea here, because corresponding parts of congruent triangles are congruent. So this is an automatic fallout of showing that these two triangles are congruent. So I want a statement about QH and RM to come out of what we're working with. So HD is not important to me. MD is not important to me right now. So I'm going to replace HD and MD. I can replace HD with QH, and I can replace MD with RM because of these congruences. And now I can just add these sections together. A quantity plus another quantity is 2 times that quantity. And then I can divide both sides by 2. So division property, that's going to give us that QH is equal to RM. And we can take that one step further and say that QH is congruent to RM by the definition of congruence. So now we have two sides that we know. If we can get some kind of an angle argument in here, we will have what we need. We have this side and this side, and we also have this side and this side. We need to have angles or another side. Since QD and RD are given to us as congruent in the beginning, we know that the big triangle is isosceles. And so we can make use of the isosceles triangle theorem and know that this angle and this angle are the same. And that's the next step that we're going to use, that angle R and angle Q are congruent by the isosceles triangle theorem. And then finally, we're going to make this argument, which I said was the easy argument, that RQ is congruent to RQ, and that's due to the reflexive property of congruence. And that gives us side, angle, side, side, angle, side. By side, angle, side, we know that corresponding parts of congruent triangles are congruent, and therefore RH must be congruent to RM, which was to be demonstrated, and we have completed this proof. We get this side through definition of congruence through the division property. We derive this. We use the isosceles triangle theorem to get these angles, and we use reflexive property to get these segments. So by side angle side congruence, we know both triangles are congruent. And so if the triangles are congruent, then RH must be congruent to QM, and that's because corresponding parts of congruent triangles are congruent. You can abbreviate this, and a lot of times you see it abbreviated. And that ends our proof.